So now we're going to go through the acquisition part, which is the actual confocal components, because the ocular we're actually using a mercury lamp, which it's pretty much exactly the same if you use a normal fluorescent microscope in your lab. Okay, keep in mind when you're in the ocular component, you're using the mercury lamp, which is a different light source than acquisition, which is using laser. So once we are ready to image, which means we found the area of interest and then we find the approximate focus, then we're going to click on acquisition. Okay, and this one is the actual confocal module. It does look like there are a few components. I assure you it's actually a lot simpler than what you think. Okay, so we're going to go through the components one by one. If it's the first time that you're using the system, then you do need to do a setup. Once this setup is saved, then you can always reuse the setup as long as your secondary fluorophores are exactly the same. So even if you change your primary fluorophore, you can still reuse the same setup. We do not require you to know how to set up for your experiment. For that, you can always ask us for help. But if in the future you do not have support like what we have here, then it's very important that you do know how to set it up yourself. And also, some people have access to the confocal microscope that doesn't have any support, then you can use this as a reference as well. For any type of confocal, not just Zeiss LSM, if you have a Leica or Olympus or a Nikon, they're pretty much all the same idea. It's just they change the buttons around to make it seem a bit harder, but the underlying process is exactly the same. Okay, so the easiest way to set up is always to use this smart setup. If you cannot see this very clearly, you can refer to the user manual, the PDF file that we sent to you, and it has step by step what I showed here. Okay, so you're going to click on Smart Setup. Okay, and then you will have this window here. Okay, this is Smart Setup window. If you click on the triangle here, you can see that's a list of fluorophore here. Okay, and that's are the most recent one. So you basically just need to choose which fluorophore you're going to use. Okay, for this, it's very important that you know exactly what secondary antibody you use, because they are going to have minor differences. So, for example, Alexa 568 and 555 and 594, they all use the same excitation wavelengths, but their emission wavelength range is a bit different. So it will be best that you know exactly which fluorophore you used. So for today, I'm going to choose to have that key. Okay, and then you see the next line showing up, so click on the triangle of the next line, and then I have, say, Alexa 48. Okay, and then the next line, say I have mitochondria, mito tracker red. If it's not showing up here, you can always search here. So I'm going to type in mito. Okay, so I have the mito tracker orange red here. So I'm going to click on here. So you can see the colors here. They're all pseudo color. Okay, so the laser itself doesn't really give a real color, and this confocal microscope is kind of colorblind. It doesn't really recognize what color it is. It recognizes the range of wavelengths that you set up to. So the color here are pseudo color, which means they're all fake. You can change it to whichever color you prefer, as long as they do make sense for you. Don't worry too much about the color. You can also change it after you finish imaging. You can change it directly on the image itself, because they're all monochrome color, which means they're all monocolor. Okay, so for here, different proposal, those are different way of taking pictures. the fastest, the first one, this is obviously by its name is the fastest, okay? And then you have best signal, you have best compromise and linear mixing. The rule of thumb is to remember we always want best signal, okay? For most of people who come to our facility, they want to image publication quality image. For that, you do want to spend a bit more time to get the best signal. So just remember, you want to use the best signal. I am going to explain what are the difference. You can see through here what's the difference. So fastest, by its name, is the fastest one. Okay, you can see for all three colors, they're on one track, which means when you're imaging the three lasers, the 405 laser, 48 laser, and 561 laser line are shining at the same spot simultaneously. Okay, so you're actually just scanning once through the field of view with three lasers. Okay, this is why it's the fastest. Whereas the best signal, you can see they're separated on three different tracks, which means you're actually imaging the same area three times. One time with the 405 nanometer laser, one time with 488 nanometer laser, and one time with 561 laser line. Okay. This obviously, because it's screening three times, it is going to be much slower. But the good thing is you are eliminating as much as possible the effect that's called beat-through or crosstalk. You might be seeing it a lot in your normal fluorescent microscope that you have access to. For example, if your DAPI is very strong, a lot of the time you can see the DAPI standing even in your green 404 that you know your protein of interest is not expressed in the nucleus, but you still can see nucleus in green, or sometimes you can even see the DAPI in red, okay? And that's called a crosstalk, and that's a false positive, and it will sometimes lead to false conclusions. So it's very important to avoid crosstalk or bleed-through because if you do have that effect, then when you're publishing your data, either you're biased or you have a difficult time to explain that your protein is not expressed, for example, in nucleus. Okay, best compromise is kind of in between those two, so you have two colors that are further apart on the wavelength spectrum. Those two are imaged at the same time, and the color in the middle, which in this case is the green color, is imaged separately. So you're screening the area of interest two times. The problem is that you can see your DAPI here, okay, and this DAPI has lower wavelengths, and a lot of time our DAPI dye is very, very strong. And in that case, it could even bleed through to your red color as well. Okay, so again, you will have bleed through a lot of times, so that's why we tend not to recommend you use that to compromise. And then linear mixing is something a bit different. Okay, so it is like the fastest, but what it does is that the software is going to subtract certain wavelengths. So for example, it knows that here you would have both green and DAPI, so we'll try to subtract DAPI part. This we tend to use it for a very specific reason. Generally, we tend not to use this because sometimes it does give an image that looks a bit too clean, and sometimes it does create question when you're submitting the picture to reviewers. So most likely we're going to use best signal, unless if, for example, you need to image very fast for your live sample, or if the live sample it's a very dynamic process that you cannot catch if you're imaging very slow. Otherwise, if you are imaging with fixed samples, or if you're imaging a live sample that's not very sensitive to the imaging speed, then you are going to use the best signal and you're going to click on apply. Okay, so it's going to ask you if a certain laser line is off, do you want to switch it on? Just click on yes. And then now you can see here that we are set up. You have three tracks because we choose the best signal. You have track 1. If I click on track 2, you can have track 2 and you have track 3. Okay, so here you have all three of them overlaid, and then here you have the information for each one of them. So if I click on track 1, this is the information for DAPI, track 2, track 3. Okay, so this white line here corresponds to this line here. This is the excitation wavelengths because we have laser, so it's not the spectrum. It's actually one relatively pure wavelength. Okay, and then this range is correspond to this range, which is the detection range. You can limit the detection range, and then you see if I move here, up there, here is moving at the same time, you can limit the detection range. Okay, and this is quite important because if you see here on DAPI, this DAPI is actually overlapped, the detection range is actually overlapped with my Alexa 48404. And sometimes this means I could, when I'm imaging my DAPI, I could have imaged some of my green 404. So what we want to do, remember to always limit the detection range of the lower wavelengths 404 so that it doesn't overlap with the higher wavelengths 404. The reason why is because the lower the wavelengths, the higher the energy, and the excitation wavelengths and the emission itself probably would excite some of your green 404, for example. Then if I am detecting all of them, then I could detect some of my green 404 being excited at the same time. So that's why we're limiting the detection here. Okay, and the next one for the green is the same thing. Keep in mind that this range is written here, so if you are not sure whether they're overlapped or not, you can refer to the range number. If I limit it, you can see the range go lower. If I increase it, you can see the range go higher. So I'm going to limit it below 56U1. Okay, if they are overlapped by 1 or 2 nanometer or even 10 nanometer, it's generally not a big deal. Okay, but keep in mind you don't want to overlap them all the way. And the other thing is the emission spectrum. This is basically a probability curve. So this tells us most of our 404 are going to land up around here on this peak. So it's very important that if you could, make sure that this range include the peak itself, because this is where you get the most signal, and then you can cut any of the ends here because there's not a lot of 404s here. Okay, obviously if we don't have a red color, I can detect all the way through because there's no 404 over there. Okay, so over here, okay, on the light path part, we have the detectors here. You can see the stage 1, stage 2, stage S1. So there are 2 different types of detectors on these lights confocal. So you have the CH and the CHS. The CH are the normal PMT detectors, and the S means it's a gas detector. All you have to know is they function differently, and the difference is the CHS is more sensitive for any color that's not DAPI and not infrared range. So, which means here, generally the rule is you want to use CH1 for DAPI, and you want to use CH2 for any IR range, such as a Alexa 4633, 647, or APC, or anything that's within that range. Any color that's in between should be on CHS because they are more sensitive. And the reason why you probably don't want to use this detector for DAPI or infrared is because this range is actually a bit narrower. The detection range is a bit narrower compared to the normal PMT detectors. You can use them. They're not wrong. They're probably just not optimized. Okay. In this case, when I set up first, you're going to see for my DAPI, it's set automatically to the CH1, which is fine. This one is set to CHS, which is fine. And then this one, though, it's set to CH2. Keep in mind that this is not wrong. Okay, you can use this and you can image this without any problem, but it's just not optimized because if you do use CHS, they are more sensitive, which means you use less laser and you might have a better signal to noise ratio. In order to optimize it, what we're going to do is we're going to manually switch this to the CHS detector, okay? The way we're going to do it, we're going to click on this small plus button here, and then you have a CHS popping up again. So we're going to manually switch it to the CHS. It's very simple. We just unclick this, okay? And then we're going to click on the CHS2. And then we're going to click on the triangle and we're going to choose exactly the same as what the software chose for us for CH2. So here I have my tool tracker orange red, and then here I can choose a red color. Keep in mind that the colors are pseudo color. You can change them to any other ones. And then the detecting range should be after should be after this line, okay? This is the excitation wavelengths. You're not supposed to detect anything before the excitation wavelengths, okay? So keep it like this. And here we are already set up for all the optimization for different colors. Now, just so we're up there, all the Zeiss microscope that we have 34 detectors. So 2 of them are CH1 and CH2, and there are 32 gas detector, which is the CHS. Doesn't necessarily mean that you can image 34 colors. What it means, the reason why we have so many gas detector is because they're spectrum array based detection, which means there are multiple detectors which are they're each responsible for a small range of wavelengths, so that would better separate the color. And when you're doing that, sometimes if you are interested in imaging more colors, for example, there are people who image 4 or 5 or 6 or 7 different colors at the same time, then the CHS would come in handy because they would help you better distinguish different colors, okay? Also, the more color there is, the harder it is to set up. You do need a lot of controls, because the more 404 you have, the more crosstalk you're going to observe. In order to minimize the crosstalk at a maximum level, you do really need to provide us with a lot of controls. Generally, you'd want the single standing control, so you want one slide with only the API, one with only 48, one with only the Mito tracker red. If you do know where the 404 is supposed to be, then obviously it's not necessary because I know what my mitochondria look like. Then you can just not provide us with negative controls, but negative control will be extremely handy if your experiment doesn't work and you're trying to troubleshoot. It's going to tell you why it doesn't work. For example, are they autofluorescence? Is there high backgrounds? Is one of the 404 not working, or is all of the 404 not working? The negative control will be very handy to show that. So we do recommend you to at least do your negative control at the beginning of the experiment, especially if you don't know where your protein of interest is supposed to express. Okay, so here you have all the different filters. You don't need to change this most of the time because when we use a smart setup, the filters are set for you. If you do need special configurations, just let us know in advance and we can help you set up manually, because manually you do take a bit more time, so we're not going to show you how to set it up manually here. If you do need to image bright field pictures, then you are going to click on the TPMT here. Keep in mind that on confocal, even if you're imaging bright field, the light source is still laser. So we are actually using, one of the laser line here. So if it's showing up here, the orange red color, and I click on the TPMT here, you see how this would show up, which means when you're imaging your mito tracker orange red, you're going to have two pictures showing up simultaneously. One is your mito tracker red, one is the TPMT, which is a bright field picture. Okay, they are two separate pictures, but they are imaged simultaneously because the bright field is actually using our 561 laser line as a light source. Okay, so you can put the TPMT to other colors as well. We generally recommend you not to put it on DAPI because DAPI use 405 nanometer wavelengths, which is quite strong and it's very easy to photo bleach your sample. So we tend to put it either on our 48 or our 561 laser line or our 633 laser line. Okay, if you don't need this, then you can unclick it. If you imaged it and you don't want it, obviously you can remove it afterwards because they are separate pictures, they're not merged together. Okay, so for this purpose, I'm going to leave it off. Okay, and then up here, again, you have the objectives. We have the objective list here. You can refer to your user manual for all the different objectives. If you have more questions, you can always contact us for it. Scan modes, we have line and we have frame. You always want to choose frame. If you choose line, you're only going to image one line, okay? So this is not for any of us who want a picture. This is mostly for the engineer sometimes to check the trajectory, okay? So we're going to leave it always to frame. Frame size, if you click on the X times Y, this is the pixel numbers within the image. For publication purpose, the lowest you can use is 512 by 512, which is 512 pixel X, 512 pixel Y. We tend to recommend you to use 1024 x 1024, but it's not mandatory, it's a recommendation. The reason why is if you use 512 by 512 and take a picture, and then afterwards you or your PI think that a part of this image is more interesting, you want to crop it, and you want to use that as a separate figure, you might not have enough pixels because generally for publication these days they want 300 DPI, so 300 pixel per inch, I think. So if you crop into a very small area, you're not going to have 300 pixel X, 300 pixel Y. Whereas if you have 1024, 1024, you do tend to get away with it. That's why we recommend 1024, 1024. However, it's not mandatory. Okay, you can use 512 by 512, and the reason why some people want to use a lower pixel number is because the higher the pixel number, the slower it's going to be. Okay, it will take longer to take one picture. But if you are publishing your picture, you don't want to go lower than 512 by 512 because you won't be able to publish it. Okay, if you want the best pixel number, then you are going to click on optimal here. Okay, and this optimal will be the best pixel number for this objective. So for each objective, the number is actually different. Okay, it's preset up inside the Microsoft itself. Probably don't want to use it for every one of your picture. It doesn't only mean that it will eat up your time. Keep in mind that any light source would have the risk of photo bleaching your sample. So if you're imaging very, very slow, it might photo bleach your sample. Okay, so generally you probably want to use 1024, 1024 for most of your acquisition. Line step, you always want to choose one. You don't want to choose any other than that. Okay, so if you choose two, what will happen is it's going to image one line and skip one line, image one line, and skip one line. Okay, what this means for laser scanning confocal, it kind of work like a scanner. So it's imaging dot by dot that forms a line, and line by line that forms a frame, which is a picture. So if you tell it to skip one line, then you're still getting a square picture like what is shown here, but you're missing half the signal in between. The image you're getting is not for publication. Okay, it's not for publication quality. Sometimes people use that to image for quantitative analysis. So they're not publishing the picture, they're actually getting data from the picture and publish it as a number. Then you could get away with line step because sometimes you want to image very fast. Otherwise, it's very, very rare these days that people want to use line step. Okay, so now the speed, okay, yearly we recommend you to keep a relative number 7 for 1024, 1024. Okay, the speed is relative. What it determines is the pixel dwell time here, which means the time required to take one pixel. Okay, and depending on how many pixels you have this times the number of pixels in total will give you approximately scan time here. Okay, so you can increase or decrease the speed. It's not a requirement for publication. However, it does affect the picture quality. If you image faster, the picture quality would go a bit lower. If you image slower, it will get a bit better. To get the balance, we generally tend to use 7 for 1024, 1024, which actually corresponds to a different number for 512 by 512. You can see the pixel dwell time is still 1.58. So it is actually the same speed, but this is a relative number. Okay, we're going to keep it at 1024, 1024. You can image very fast. If you have a live sample and you need to image very fast, then you can obviously click on max to get the maximum speed. But keep in mind that the faster it is, the crappier your picture is, the better, the slower it is, your picture will always look better, which is always the rule for confocal. So averaging, this is how many times you want to image the same area. The reason why you want to keep repeat imaging the same area is because when you image the same area several times, the software it's going to try to see where is your background and where is your signal, and it's going to do a mathematical computation to increase your signal to noise ratio. So averaging number is how many times you want to average. You have from 1, which is no averaging, all the way to 16. Generally, for a fixed sample, we recommend a speed 4, a number 4, which means we're imaging the same area 4 times. Okay, if you are imaging, say, a tile scan, or especially if you're imaging a Z-stack, sometimes you want to use averaging 2 or sometimes even 1, okay, because you don't want to photo bleach your sample. That's the rule of thumb, okay. Otherwise, if you have a fixed sample that has very strong 4 doesn't tend to photo bleach, averaging 4 really do give you a very good quality imaging in terms of signal to noise ratio. There are sometimes people use 16 or 8. Okay, obviously it will be slower because you're imaging the same area so many times. This is usually used when people are imaging tissue sections, and they tend to have a lot of background or noise or autofluorescence, and people do tend to use higher averaging number. If you do have a relatively low autofluorescence or backgrounds, 4 is more than enough. Keep in mind that averaging is not mandatory either, okay? So you can use averaging 1, but keep in mind the faster it is, the picture wouldn't look as nice, okay? So I'm going to keep it at 4 here. Averaging mode, you can always choose line. You have line and frame. So what line means is you're imaging the same area one line 4 times, okay? And then you move to the next line, and then it goes through 4 times, and then you move to the next line 4 times. Whereas if you choose frame, then it means you're going to image the whole picture, and then it goes back to the starting point and image the whole picture. Okay, line will work for both live and fixed sample, and frame would only work for fixed sample. So we generally tend to choose line, but if you always use fixed sample, you can choose frame. There's no difference. Okay, I'm going to leave it line here. Now, the averaging method, you have mean and you have sum. You always want to choose mean because it will increase your signal to noise ratio. Sum, you will add up everything, so you do have higher signal and you have higher noise, so we tend not to use it a lot. Okay, so choose mean. Bit depths, this is very important if you want to publish your picture. Most of the time you want to use 12 bits or 16 bits, okay? 8 bits is sometimes not allowed, well, most of the time not allowed for publication. What bit depth is a degree of color between pure white to pure black. For example, if I have my DAPI, my weakest blue color would be, say, a white color, my darkest blue color would be a black color. If you choose 8-bit, you have 2 exposure 8 times of different blue color from all the way from the white, the weakest blue, to the darkest blue, which is black. Okay. If you choose 12, it will be 2 exposure 12 times. If you choose 16, it will be 2 exposure 16 times. This does not increase your exposure time. So the exposure, sorry, does not increase your acquisition time. Okay. The acquisition time will still be the same, but the 16-bit will have a bigger file than 12-bit than 8-bit. Keep in mind, you can always convert a higher bit depth to a lower bit. Okay. For example, a lot of quantitative analysis, you can only do the analysis on 8-bit picture, but you can take a 12-bit picture and you can convert it to 8-bit, whereas you cannot do the reverse. Okay. So please keep in mind that you need at least a 12-bit, if not a 16-bit. But generally tend to recommend to use a 12-bit because a lot of the older analysis software crash when you try to open a 16-bit picture. So that's why we tend to recommend 12-bit, but this is totally up to you, and you can always convert a 16-bit to a 12-bit afterwards if it doesn't work. Okay. Direction, you have unidirection arrow and you have bidirection arrow. Okay. So usually you want to start with bidirection arrow. What this means is that when you're imaging, remember we're imaging point by point that forms a line and line by line that forms a frame. So if you have bidirection, say if this is the area, the laser is going to image this way on the way back. So back and forth 2 times because we choose averaging 4. So image this way on the way back, this way on the way back 4 times now, and then move to the next line and then this back and forth. Okay. If we choose unidirection though, it's going to image from left to right, comes to starting point, left to right, starting point, left to right. So if you choose bidirection, it will increase your acquisition speed, so you image much faster and the quality is relatively comparable. Okay, so that's why you always want to start with bidirection. Just keep in mind, a lot of time, especially for the older confocal microscope, you don't want to use bidirection because it does has a possibility of creating an artifact. Okay, but the artifact is very easy to observe. You're going to either see stripes inside your picture, or you're going to see a bit of that fuzzy picture line, like if our microscope is drunk. So it's very easy to observe the artifact if it is because of bidirection. So we tend to recommend you to use bidirection because from our observation, our microscope doesn't tend to give any artifact if you use bidirection, and it will cut your acquisition time by half, which make it a lot faster and a lot more productive for you. So that's why we recommend you use bidirection. Okay, so now the scan area. This area is the area that you're going to image. You can zoom out or you can zoom in. This is not a digital zoom, which means it's not actually zooming in inside the picture. It's actually the microscope itself. Okay, so you can image a bigger area. The biggest you can go is zoom 0.6. Oops, sorry. Let's try again. 0.6. Okay, so this area is a lot bigger. You can see the actual size here. Okay, and you can see the pixel size, which means the actual size per pixel. Okay, you're going to see if I image zoom 0.6, the resolution actually decreased a bit because the pixel size is 0.22. If I use 1, then the pixel size is 0.13, which means it's actually a higher resolution, okay? But if you want to image a bigger area, but you don't want to change the objective, you can always use this to image the bigger area, okay? The other thing is you can move this around, okay? For example, if you want to image a neighboring picture, you can drag, if you want to image a neighboring area, you can drag this around as well. You can actually also rotate this, okay? Keep in mind the only area allowed is here, so if you do 0.6, you cannot change, you cannot move it around as much, and you can certainly not rotate it, okay? Because this is a maximum imaging area that we are that the microscope allows us to do, okay? So say if my cell is very long, then I can rotate this to fit that one cell. Or a lot of time, if you are imaging tissue and you cannot get the tissue to be all parallel to each other, then you can use this to image them parallel. So that way that all your pictures are imaged at a certain direction of the tissue. So it will look a lot cleaner when you publish, okay? So I'm going to click on Reset All to reset this, okay? And then the last part, these channels, this is very important. All of the other parts that I showed you, really you don't have to touch as long as we set it up. And once you set it up and we take a picture and we save the picture in the original format, which is either LSM format or CZI format, the configuration is actually saved within the picture itself. You can open the old picture that is in the LSM format or CZI format and retrieve the configuration within it. The only thing though is for the channels part, we do really need to understand it, otherwise we won't be able to image it properly, okay? So next we're going to talk about how to image, and we're going to talk about the channels part.